Hey class, I hope your exams are going well. I realized that I kind of shortchanged you a little bit on our review last Thursday, um, and it was a little bit intentional. I wanted you to feel a bit of that panic. Uh, it can be inspiring from time to time to not have all the answers and to have to figure out what you're going to do. But more than abandoning you or you know leaving you in despair, I wanted you to get a sense of what it would be to uh, how you would account for your first step whenever you have to search for a solution. Um, and so, I hope you felt confident, and if not, I hope you used the panic and dread wisely. I thought we could go back and we could spend today's lecture going over the review, the solutions, which I posted, I believe, last night, and we can discuss a couple, maybe three light proofs or just topics in general, and that'll be it. So today's lecture should be pretty short. Let's jump into the review, and then we'll come back and cover the other topics. Okay. So for the first one, we're using Dijkstra, and um, if you remember the problem, so these are the review solutions. Okay, good. We're not discussing the actual exam. It's a shortest path. So what's the shortest way to get from D to E? Now I made no requirement for you to show your work, so if you can just find the solution, that's fine. But I did want the exam problem to be sufficiently annoying enough that you would consider using Dijkstra in order to guarantee your solution. And so you can see from the solution that you can go from here to here to here to here to here, or from here to here to here to here to here. And they both have the same total weight, so either way. But yeah, it is at least guaranteed to converge to a solution with Dijkstra. In particular, because Dijkstra essentially has you work out uh, the shortest path to every node in the graph from your starting point, and then that eventually tells you what the shortest one is to E. Um, so it does so by exhausting vertices and edges, at least that are connected to your starting point. Um, it yeah, there's really no way around it. You have to consume both, and so the wisdom of Dijkstra's algorithm is that it gives you the order necessary uh, to grow your solution set, so that you're guaranteed to deal with shortest paths. And so, um, if you have a starting point with Dijkstra, then you can choose the shortest path from there, and you say, okay, well, I'm going to have some minimum weighted distance, and the best you can do in getting out of Dodge is this path to C of distance 1. And so the furthest you can get from D and the quickest, with aside from C, the next best you can do is to get to G. And so that's just the total weight of 3. And so you continue going about and casting for the shortest distance that you can do, the best you can do, essentially, from each one of these vertices. Or sorry, not from each vertex. The question is, okay. So I've been watching a lot of Homeland, so forgive me if it's an inappropriate reference or whatever, or a different reference. But let's say, yeah, you're on the lam, you're running, right? And so the leaving from D, you're starting in, if this is your starting city or whatever, and you're just looking at bus passes, and you're either accounting for the furthest you can get in the for the least number of dollars, in terms of bus trips, or the least number of days. So how far can I get? How fast? And so if you're going from this city to this city, then this costs you 1 day. From this city to this city, it costs you 2 days. If you wanted to get here, you could get there directly in 5 days. And then if you wanted to get here, well, you can take the 2 separate trips to get here in 3 days, and then go spend 3 days getting here, or you can spend 4 days, or you can go from here to here in 4 days, and then a 5th day would get you here. And so that turns out to be the best bus route to get from D to F. And then to get from D to A, the straight shot, 1 day, 3 days, 2 days is the shortest route to get here. And so at this point, we've solved every node except for E. We have the shortest value. And so you can either go from D to A, and then from A to E for a cost of 3, or from D to F, and from F to E with an additional cost of 4. And it turns out that in terms of days traveled, spent on the lam to get from D to E, then either route is as good as the other. So there's 2 different solutions to this. But yeah, it's essentially solving for shortest path to every node, to every vertex, or whatever. But it's consuming all vertices and essentially all edges to get there. Strictly speaking, it is able to discard certain edges if it's never to your advantage. So let's say, for example, that we go from that we solved from D to C, G, and H, and there's a direct path from D to G with a cost of 50, so it's more expensive than either route. Well, once this node is solved, we never have to actually find a purpose for that additional edge. We've considered it, but it connects 2 vertices. So one of them's the source, but it connects to a vertex that's already been fully solved. So we already know there's no better way to get there, because essentially we added vertices only whenever it was the next closest city. So as we were mapping out our route, we were only consuming it if it was the next closest city. And so we don't necessarily have to consume every edge, but so you can think of Dijkstra as a vertex-centered algorithm. So in that regard, it's also possible to never consider a particular city. So if we're considering from D to E, it is certainly possible, and probably even likely if the vertices are far enough removed from each other, to get the shortest distance to every city on the map from some source. But if we're only looking for the shortest path from D to C, well, we started with D, and then we expanded our route by just consuming the next, the cheapest acquired vertex, or so the closest city by days traveled, and that was C. Well, at that point, we're already guaranteed that that's the shortest path, because that's the the closest accessible vertex from D. So we wouldn't even have to consider anything else if we applied Dijkstra's algorithm properly. So do you have to use Dijkstra? Do you have to show your work? No. And you even have a program that'll compute the shortest route for you if you want to use that. In which case, I would applaud you for learning how to use it, learning how to apply it. Or if you're one of those going for the extra credit, even better. Okay, so the second one, prim's algorithm to find a minimum spanning tree. So for this one, you can use prim if you know how to generate it on your own. That's fine. But the point of prim and crewskull is that they give you algorithmic solutions. They can guarantee that what you find is actually a solution. But for the ones that we're considering, even the one on the exam, it's certainly possible to just intuit the solution. So if you're good enough, but how are you going to prove that what you have is the minimum spanning tree? I suppose you could take a guess and get it wrong, but hopefully you'll take this chance to actually apply and kind of reinforce it. Just so you're considering multiple problems from multiple angles, but explicitly you don't have to show your work. So for this one, prams is the vertex centered one. So you start with the minimum edge, and then you can grow from either vertex. And so the shortest edge from here is both this 3 and this 3. And so you can see in our solution we never end up using the 5. We've already acquired B at this point, and the cost to C is extremely expensive, so we probably won't grow in that direction for a while. And then the next cheapest way to grow our tree is either this 7 from D or this 5 from B. So we consume this edge, and now we have A in our tree. And so the only vertex we have left to reach is C, and we can either add it by a cost of 8 or by a cost of 21. So we choose the cost of 8. And so it's pretty simple. You should be able to apply it to the exam as well. But I certainly understand that whenever you're learning things as well, it's quite easy to panic. Okay, and so for crewskull, find the minimum spanning tree associated to it. So it's crewskull's was the edge one. So you just keep adding edges, and so long as it doesn't create a circuit, then you're fine. The cheapest edges were the ones, right? So this one, B to C, C to D, and then from D to A, and that was it. So that one, it's not as obvious because it's not graphical, but it still represents a graph. So if you wanted to map it out, and then consume the edges appropriately to construct the spanning tree, that's fine. And so it's certainly easier whenever you're looking at it and you're consuming the edges, so that you can make sure that you're not creating a circuit or a non-tree graph, because you can easily see if you've created a loop, but programmatically it's a little more difficult, all the same. Okay, so for the trees, we're given a tree and then we're asked what would be the output for it, and we're given this callback. And so we covered an example where we were traversing a tree and we were invoking this callback. And so all it does is it prints to the console this string, node ID, and then space, colon, space, and then some value. And the value is going to be whatever's listed here. From there you have to know what a post-order traversal is. And so post means that it covers both children before it gets to the parent. We'll leave pre and in order traversals up for grabs. And so, yeah, so we cover the children left to right, and then the parent, and then children left to right, and then the parent, and then the parent. There we go. Okay. So now breadth first traversal lexicographic ordering. Yeah. Okay. So so this is just alphabetically sorted, right? Lexicographic, but it can be a little more elaborate than that. But typically, this is just going to mean that you're going in alphabetical order. So you compare the first letter and the second letter and so forth. But when there's only one letter, it's the same. We could sort it by ASCII representation of the character or whatever. Okay, so breadth first. What are we doing? Well, we start with A, and then we iterate over the children, and we add them to a queue. So B, C, D, E, according to lexicographic ordering. This has 4 children. So this was the next one in the queue. And we ignore any vertices that have already been consumed. So E is already part of the tree, and it's owned by A, as is D, and A is already a part of the tree. So the only new vertex that B can contribute is F. And that's it. At that point, we've already spanned the entire graph. And so that's it. We have our representation. Okay. And then we went over this example last time. Okay, so let's jump back. We'll cover 3 quick topics, and then I'll let you get back to the exam. Okay, so I wanted to talk about addition and multiplication by 2. So it's pretty simple. Hopefully next time we'll have a chance to explain why I'm having you learn how to add and multiply by 2, and then maybe that one will be a little more interesting to cover than this one. Okay, so I wanted to point out that multiplying any number, so this is a decimal representation, so 5050 by 2 is the same as adding 5050 to itself. And so you do it column by column. 0 plus 0 is 0, 5 plus 5 is 0, carry the 1, the 1 applies here, okay. And then 5 plus 5 is 0, carry the 1, and the 1 comes down here. And so, okay, so now let's do it over here. So this is a binary representation, 1 0 1 0. So this is 8 plus 2, and this is the number 10. So we're adding 10 to itself, or we're multiplying by 2, which is the same as adding it to itself. So same rules, right? There's no tricks except the number that we count up to is we're only counting up to 2, and then anything after that we carry the 1, or if we have overflow we carry the 1. So 0 plus 0 is 0, 1 plus 1 is 0, carry the 1. Comes down here, 1 plus 1 is 0, carry the 1, comes down here. Well, this, if you'll observe, is the same thing that we started out, 1 0 1 0, but we've added on a 0. So just like whenever, if I had you multiply 75 times 10, the number's 750. It's pretty easy because we're in base 10. When you multiply by 10, you're just adding a 0 to the end. 75 times 100 is still easy. 75 with 2 zeros tacked on. And so the same rules of arithmetic apply in base 2. So if you multiply by 2, then you just tack on a 0 to the end. If you multiply by 2 squared, or 4, then you would tack on 2 zeros 2 cubed or 8, you would tack on 3 zeros, and so on and so forth. And so this is how we use, we just call this shifting left and shifting right. So you just feed in zeros on, if you shift left, right? So this is this number shifted left by 1, so we've just tacked on a 0 to the end. Then that's the same as multiplying by 2. If we had shifted left by 2, then it would be the same as multiplying by 4. If we'd shifted left by 3, then it would be the same as multiplying by 2 to the 3, or 8, and so forth. And so, it's really easy to multiply by 2. You're just tacking on zeros to your binary string. And division is the inverse operation of multiplication. So dividing by 2 is just the opposite. So instead of shifting left, which we did for multiplying by 2, we shift right, and that divides it by 2. So these integer representations, it's really easy to divide by 2. Okay, so simple enough. We'll hopefully be able to come back to a more interesting example next time. Okay, so I said we'd start proving stuff, so let's do just a couple of quick concept proofs, and then you can get back to your exams. Okay, so the first one is the Harmonic series. I don't think we've covered it this semester, but if we have, just humor me for the next couple of minutes. Okay, so this is fifth. Okay, so whenever they started to explore limits, this concept that you can have these vanishing terms, and it vanishes quickly enough to actually have the whole thing add up to something, so you can have an infinite number of additions that doesn't add up to infinity. The next question is it always true that if at the limit this term vanishes, so if 1 over n, it goes to 0, if we add something that goes to 0, is it true that the entire series adds up to something? A reasonable assumption is, yeah, sure, of course it does. The last term goes away, so of course it adds up to something. But then the question was, what? And so if you consider this series, where you're just increasing the denominator by 1 each time you increment the denominator by 1, it seems like it gets smaller, like it's growing, but slower and slower. So when does it stop? When is this thing eventually going to stop? And the answer is that it doesn't ever stop. It grows on forever. I believe the antiderivative of 1 over x is the natural log of x, and that does go to infinity really slowly. It's but it goes to infinity. So none of this was really known properly when they first started exploring limits, and I have no idea who first proved that the harmonic series diverges. But the question of okay, if the terms all vanish, does it add up to a thing, or does it add up to gibberish? Does it go off to infinity? And it's gibberish, and the way we prove it is is inductively. Okay, so we end up breaking this down in terms of sets the size of the power of 2. Oh. So we set the size of 1, 2, 4, and then 8, and so on. And then we'll see that the pattern holds. So this is the sum of this set is greater than or equal to 1/2. So you'll see why we use the inequality later. And so here the sum is greater than 1/2, and that's because well, a quarter plus a quarter is a half, and a third is larger than a quarter. So when you add it up together, you get something that's larger than a half. And then the next set has 4 elements, each greater than or equal to 1/8. So you get a sum that's greater than or equal to 4 times 1/8. Well, 4/8 is again a half. And we have an infinite number of such sums that we can make. And so we can add 1/2 an infinite number of times. Now it takes us twice as many terms to get there each time. So it gets slower and slower that we're getting to that 1/2, but we're always able to achieve it. And so there is no maximum number. We can add 1/2 forever. And so this series turns out to diverge. Now this is just this is an argument, not strictly speaking a proof, but the argument is really the high level, the essence of the proof. It's the steps you'll take to formally show that something does or doesn't happen. And so I can tell you that anything, so this is it. If you have a series that is term by term smaller than this, then it actually adds up to a thing. So this is essentially the smallest way you can reach infinity by adding up numbers term by term. Well, and I say that even that isn't necessarily true. So if you just cut the numbers in half, then so you have and so forth. Well, now your groupings are no longer adding up. Oh, you can barely see that. Sorry. So your groupings are no longer adding up to 1/2; they're adding up to a fourth, but the same sets or whatever. Well, you can just as easily add a fourth an infinite number of times to get to infinity, but yeah. So so the sequence is represented. by this, and so it's here we have that r is equal to 1, and if we add them up, then we get 1 over 1, then 1 over 2, then 1 over 3, and so forth, and so we recover this series. If we have that this is squared, then it adds up to, I want to say pi squared over 6. I'll have to verify that. But yeah, that'll actually be a fun proof. Maybe we can go over that one. So if this exponent is 1, it diverges. If it's 2, it converges. And so if it's larger because it's in the denominator, then it's shrinking even faster than the sum of squares, which adds up to a thing. So we know that everything larger than the square is going to add up. And so there's this question of, well, what about the stuff between when this is a power of 1 and a power of 2? Is there some cutoff? And it turns out that, yeah, the cutoff is whenever that power is 1. That's the only one that diverges. So if you have any power, so you can't, it's not enough to divide term by term the sequence by some constant, because you'll just get to infinity slower. But if you raise the denominator to a power larger than 1, and infinitesimally smaller than 1 is sufficient, then you get something that adds up to a thing. But the closer you get to 1, the closer that sum is going to get to, it never gets close to infinity, but it's going to get really large the closer you get to 1. Okay, so that's the harmonic series, and that's an argument for the divergence of the harmonic series. You probably need like another 2 or 3 lines of exposition to actually fully finish it off. But that's the essence of it, right? So you have these sets and these subsets of the sequence, and the subsets add up to a finite number, and you can construct an infinite number of these subsets just by grouping them of size power of 2, in a certain order. Okay, so there we have it, a high-level argument for proof. And then we'll have one more high-level argument, and then you can be done with me for today and focus on the exam or whatever else you have going on. Okay, so we said that one-to-one correspondence is an argument for proofs. So let's see what we can do about that. All right. So we have a set. Burning through markers here. Okay, so we have a set. And I want to know how many different ways I can group these sets. So how many different combinations of subsets are there? Just pulling elements from these. Okay, so we'll index these, zero index them. So 0, 1, 2. Okay, so let's say that an item is included if we'll use Boolean arithmetic, right? So is included so we have a function, we pass it an index for our set, and it returns, if it's included, it'll return 1, if included. So if our subset includes whatever item is at index the one passed it as the parameter, it'll return a 1, and if it's not, then it'll return a 0. So you can think of this as true and false. So is included, true, or false, or whatever. Okay, so let's ask the question 3 times. So okay, so for every item in our set, or for every index less than the length of our set, so we have 3 items, so our length is 3, and so we want the indexes from 0 to less than 3, so it would be 2. We need to do something to represent this. Okay, well, we have something, we have an output that'll tell us, that's sufficient to tell us whether or not an item is included, and it's binary. It's 0 or 1. So it would appear as though we can use a binary representation to indicate whether or not an item is included. So our subset our subset can be constructed from a bitwise OR operation. And so we go through every item in the index, and so we would have to have something else is happening in this function to tell us whether or not that item is included. So something else is giving you the information for whether or not it's included in the subset. And so we ask the function that knows what the subset looks like, or what the construction of the subset looks like. So maybe we have this function and it's returning so given some student number within a class, whether or not the student is passing, and you're looking for the number of passing students, or more likely you're looking for the number of at-risk students. So you could correspond student ID or student number in this class to a subset of the whole, and you can store it in a binary representation no smaller than the size of your set. So a 32-bit binary number would be enough to represent this 3 set. A class of 33 in this example would not store into a 32-bit number. You'd have to use a 64-bit number for that. But the point is that you can use a binary number to store it. So you only need this. You only need a bit and a place or whatever. Well, you can number these. So we can create this one-to-one correspondence between the index within the set and the binary representation of a number. So So this is essentially going through and and filling out this binary representation. So we've created a one-to-one correspondence between a set, and then through the construction of a subset, we're able to map it to a unique representation of n bits. So either it is in the subset or it is not in the subset. And so through this correspondence, we at once have an answer to our question: how many distinct subsets can we construct from a set of n numbers? And it's 2 to the n, right? So we have the subset, we have the empty set, which is always a subset, where we haven't included any elements of the set. And then if the set is of size 1, then the first index in our set would correspond to 2 to the 0. So it's either 1 or 0. And then inclusion of the 1 indexed value in our original set would correspond to this one. Inclusion of the 2 indexed value of our set would correspond to this one. And then just counting, right? So counting through our binary representation. How many unique values can a binary number of this many bits represent? And it's 2 to the n. So you can use bitwise logic as an argument, or even a practical way to represent some of these values. So I thought that was pretty cool. So there's a lot of really cool things that you can do with binary logic. You have to go a little bit out of your way to find them at first. I was fascinated with binary arithmetic whenever I was an undergrad, but it was a while longer until I found other practical uses for it. But I looked everywhere for ways to use it because I just thought it was really cool. Okay, anyway, I've already gone over on how long I wanted, but so this is an example of using one-to-one correspondence as an argument for a proof. So how many subsets can you construct of a set? Well, you create a one-to-one correspondence with the bits within a binary representation of a number, and then the known number of values that a binary string of that many bits can represent is your answer. So it's 2 to the n. Okay, cool. So today's was more about just making these high-level arguments, and at some point we will actually dive into proving stuff, but I want to make a point of trying to tie it all together a little bit. So some of the stuff we learned originally, some of the data structures that we've studied, and then using it to create these visuals and stuff, programmatically when possible, to assist in constructing some proofs, and then just some basic proofs as well, because it's a bit of a learning curve at first. So I'm aware that it can be difficult, but I don't know. You just endure the discomfort and you keep practicing. And so long as you struggle a little bit, if you don't struggle, if you get it right off the bat, that's great. But if you don't get it, then it helps to retain the information if you bear the pain a little bit. So you have to at least get to the point where you're thinking, what is the answer? And then when you get there, then you're ready for the answer. But if you just glance at it and say, I don't know, something probably, then you're a little less likely to retain the answer. So yeah, do try, whenever we're going through the proofs or whatever. For the homeworks, whenever I figure out what it is that I want to assign for these homework problems, try a bit. Go through the struggle a little bit, and then whenever you get the answer, it'll you'll be in a better place to take it in and absorb the new perspective that's been offered to you. So, okay, best of luck on the exams. I'm sure you're all going to do great. If you have any pressing problems or anything, email me and let me know. Otherwise, have a good weekend, and we'll talk on Tuesday.